Hello everyone, my name is Hani Sadiq and I will present to you my thesis work. It's about the sizing of a fuel cell stack and battery system for a fuel cell hybrid vehicle using dynamic programming and Pareto analysis. It is about the most efficient cost-effective mix of fuel cell and battery powered hybrid vehicle. I will start with an introduction that includes a brief on the literature review that then I will explain my thesis objective in details. After that, I will present the system model and talk about the energy management system, the drivability constraints, and the driving cycles. These determine the feasibility region of power sources sizes in addition to the sizing methodology. At the end, I will present my results and my conclusion. Our environment today is plagued by pollution that is primarily caused by carbon dioxide emissions. A major source of these emissions comes from the internal combustion engines relying on fossil fuels. The world committed to reduce climate change by relying more on green and renewable energy. One of the types of green fuels that can be used is hydrogen under the condition that it is produced from renewable energy sources. Vehicle manufacturers are competing to produce more environmentally friendly vehicles, following extensive work done by research and development units. Electric vehicles have been brought to the market as such solutions. The limitation to currently marketed powered vehicle can be mitigated by the introduction of fuel cell hybrid electric vehicles relying on a combination of batteries and fuel cells that use hydrogen from renewable energy sources. As of 2016, three models of fuel cell hybrid cars became publicly available at a very high acquisition cost and only in select markets: the Toyota Mirai, the Hyundai Nexo, and the Honda Clarity. Extensive research still needs to be done to reach the most cost-effective, economically feasible, and efficient solution for mass production of fuel cell hybrid vehicles. The difference between an electric vehicle and a fuel cell hybrid vehicle is mainly depicted in five factors. The first one is the number of sources. In the fuel cell hybrid vehicles, we have two sources: the fuel cell, which is an on-site generator of electric power, and the battery. The second factor is the complexity of the energy management system. The fuel cell hybrid vehicles require a more complex energy management system as we have two power sources. The third factor is the cruising range. The fuel cell hybrid vehicles can travel for longer distances. The fourth factor is the energy capacity of the power sources. The energy capacity of compressed hydrogen is 200 times greater than the best energy capacity of a battery. This saves significant spaces and weight in the vehicle. And the final factor is the time needed to recharge or refuel a vehicle. An electric vehicle needs at least 30 minutes to 5 hours to recharge depending on the cruising range. On the other hand, it takes 2 to 3 minutes to fully refuel a fuel cell hybrid vehicle to travel for a long range. The objective of my thesis is primarily to find the lowest operational cost per trip for a hybrid fuel cell vehicle. First, I determined the most suitable battery type. I used the tunnel dynamic programming technique for the optimization of the energy management system of the vehicle. I conducted the sizing optimization for the power sources, taking into consideration three drivability constraints. All the work was simulated on 3 driving cycles, and at the end I checked the cruising range of the vehicle using 5 kilograms of hydrogen. I analyzed the 4 forces applied on the vehicle during a trip: the aerodynamic drag force, which is caused by the compression of air on the frontal surface of the vehicle; the gravitational force, which is caused by the load of the vehicle, and it only affects the movement of the vehicle when traveling on an inclined road; the rolling force, which is caused by the friction of the wheel on the road surface; the acceleration force, which is required for the acceleration of the vehicle. These are the modeling equations of the vehicle, and in this table on the right, I'm showing the vehicle variables and parameters. The diagram shows the power propagation in the system from the wheels to from the power sources to the wheels. The power is affected by the transmission and motor's efficiencies, which are also taken into consideration in this model. Driving cycles are mainly used by the vehicle manufacturers and researchers to test the vehicle fuel consumption and polluting emissions. They are produced by organizations from different countries by gathering statistics about the driving habits of the drivers. The driving cycles I considered in my study are the highway, the FUDS, and the NEDC. The table on the left shows the main characteristics of the three different driving cycles. And the diagrams on the right show the speed profile of each driving cycle over the time of the trip. There are many types of batteries currently in the market, but lithium-based batteries are becoming more popular as they are characterized by their high energy density and lightweight. The most commonly adopted ones are the ones shown in the table here. Three of them are currently used in automotive application: lithium nickel manganese, lithium nickel cobalt aluminum oxide, and lithium titanate. The one used in Tesla cars is the lithium nickel cobalt aluminum oxide. For fuel cell hybrid vehicle application, battery power density is what matters the most, unlike electric vehicles, where large energy storage is required. However, as we need high power to be available, the batteries are sometimes oversized from an energy capacity perspective. Lithium titanate might be the most suitable battery for the study for many reasons. It has the highest discharge rate, 30C up to 5 seconds, the longest life cycle, 3000 to 7000, and it is the safest lithium ion battery in the market. The only disadvantage is the high investment costs. It is $1,005 per kilowatt hour, but if this cost is divided over the life cycle, it becomes very cheap. The energy management system is used to monitor all the components, data measurements, and it controls the power split between the fuel cell and the energy storage. It is connected to each component in the vehicle. The power control is unidirectional for the fuel cell and bidirectional for the battery and the motor. The reason for using a bidirectional power controller is to enable the vehicle to capture the energy from regenerative braking and store it back in the battery. The amount of regenerative braking is significant, specifically in the driving cycles characterized by many stop-start patterns. This amount will be clearly presented in the results slide. Tunnel dynamic programming is an enhanced version of dynamic programming through which the number of states at each time step is fixed. This enhancement eliminates the dimensionality problem of dynamic programming. The objective function of the optimization is presented on the left, and below it are the constraints that need to be taken into consideration. During dynamic programming, the system tries to find the cheapest path when transitioning from the states at a time step to the states at the next time step. When the last time step is executed, the lowest cost is marked and saved. The path of the lowest cost is traced back to the initial time step, and the optimal path will be determined. The algorithm here shows the forward path and the backward path tracing. The graphical presentation shows the forward path in light lines and the backward path in dark lines. The study will be performed on two operation modes for the energy management system: the charge depleting mode and the charge sustaining mode. In charge depleting mode, the energy management system relies more on the battery, which leads to the continuous reduction in the state of charge of the battery. The fuel cell operates in two cases: when the battery gets fully depleted or when the demand power is higher than the power of the battery. Since the cost of the power supplied by the battery is cheaper than the power supplied by the fuel cell, the system will automatically operate in charge depleting mode if no modifications are done to the objective function. In charge sustaining mode, the energy management system relies more on the fuel cell. The battery only supplies power when the demand power is higher than the power capacity of the fuel cell. The charge sustaining mode can be achieved by adding a weight to the cost of the battery only on the optimization function and not in the cost calculation. The aim is to make the battery look more expensive during the calculation, which increases the reliance more on the fuel cell and thus keeping the state of charge of the battery in the desired range. Three drivability constraints are taken into consideration: the maximum speed of 150 km per hour, the gradability constraint, which is represented by a maximum speed of 110 km per hour on a 5% upward inclined path, and the acceleration constraint, which requires the ability of accelerating from 0 to 100 km per hour in 12 seconds. The first two constraints help to determine the minimum allowable size of the fuel cell, and the third one helps to determine the minimum power sizes combination of the minimum motor power. These plots show the variation in the trip cost against the variation of the battery capacity for each power capacity of the fuel cell. The trip cost is presented on the y-axis and the battery capacity is presented on the x-axis. Each color in the plot represents a fuel cell power capacity as shown in the legend in the upper right corner. The resulting Pareto front shows the most optimal solution for each driving cycle. So for the highway, the best combination is 30 kilowatts for the fuel cell power size and 4.5 kilowatt hours for the battery energy capacity. And the results for the other two driving cycles are presented below them. While these values are the most optimal, we still need to check their feasibility. The contour plots show a different presentation of the results. They are used to show the level of operational cost against the variation of both the battery capacity and the power of the fuel cell. The battery capacity is presented on the y-axis, and the power of the fuel cell is presented on the x-axis. The color of the contour plot indicates the operational cost level. The color bar shown on the right side of each plot presents the value corresponding to each color. The red line inside the plot represents the maximum speed constraint. The yellow line represents the plot represents the maximum acceleration constraint. The results that we found before don't exist in the feasible region. So the most feasible and cheap sizes combination are now for the fuel cell power size 35 kilowatt and for the battery energy capacity 4.5 kilowatt hours for the highway, for example. And the same applies for the FUDS and the NEDC. The plots here show the power allocation and state of charge for each driving cycle in charge depleting mode. The black dashed line represents the power demand of the vehicle. The red line represents the power supplied by the battery, and the blue line represents the fuel cell power. The power is mainly supplied by the battery, and the battery keeps on depleting until the trip ends. The initial state of charge was 80%, and the final state of charge was 4.97% for the highway, 0.54% for the FUDS, and 4.86% for the NEDC. The total energy supplied by the battery is greater than the energy supplied by the fuel cell for the charge depleting mode. The plots here show the power allocation and the state of charge for each driving cycle in charge sustaining mode. The power is mainly supplied by the fuel cell here. The initial state of charge was 80%, and the final state of charge was 78.01% for the highway, 84.79% for the FUDS, 76.66% for the NEDC. The total energy supplied by the fuel cell is greater than the energy supplied by the battery. This table summarizes the simulation results for the charge sustaining mode. The cruising range using 5 kilograms of hydrogen is 511 kilometers on highway, 411 kilometers on FUDS, and 439 on NEDC. The importance of regenerative braking is clearly shown here. It contributed 7 to 21% of the total energy required for the trip. The study was also performed on more realistic driving cycles combination, which consists of driving 55% on the highway and 45% on the in the city or on an urban driving cycle. In Lebanon, for example, when I go to university, from my house, the first part of the road is highway and the second part is driving through the city. So this is a realistic combination of driving cycles. And the best sizing combination was found to be 35 kilowatt for the fuel cell power and 4.5 kilowatt hours for the battery capacity. In conclusion, achieving the lowest operational cost with the best performance in terms of meeting the drivability constraints was to use lithium titanate batteries. Achieving charge sustaining mode of the vehicle was done by adding a battery cost weight to the objective function. The most optimum and feasible solution for each simulation were determined, and the cruising range of 5 kg of H2 used was checked on each driving cycle. And at the end, the importance of regenerative braking was clearly shown. Thank you.